Okay, so team, in the last session, we looked at decrease and conquer, right? And we defined it and we said there are three types of decrease and conquer: decrease by constant, decrease by constant factor, and variable size decrease. So here we said that there will be only one subproblem that will be executed in decrease and conquer, and that subproblem will have a size, say n dash is equal to n minus c, then it is decreased by constant. N dash is equal to n divided by c, then it is called decrease by constant factor, and then n dash is equal to say n minus c for some variable c, not a fixed c, then it is called variable size decrease. And we looked at a couple of algorithms, right, for decrease by constant, and we looked at one problem and algorithm for decrease by constant factor. This was the second problem for it, Joseph's problem. What we will do is we will skip this problem. We will directly move to variable size decrease. So we will look at selection problem first, right? Because it is extremely important. That is one of the deathbed problems or algorithms you need to know, remember, right? One of the most famous problems in computer science. And once we finish that, we will come back to Joseph's problem. Because as we have already seen one example here in decrease by constant factor, this is the second problem. But before looking into the second problem, let's cover the most important problem, the selection problem, right? So that would be a good example for this variable size decrease. Okay, let's start with the selection problem. What are we selecting? What is a selection problem? You are given an array of n elements, say a of 0 to n minus 1, or a of 1 to n, whatever. Or you could be given a streaming set of elements also. Do you know what is streaming algorithms or something like that? So assume you're working with, say, Facebook or Google or whatever. The data will be coming in a stream, right? The first web page, second web page, third web page, or maybe the first post, second post, third post. It's not necessary that you have to store each and every post there. Maybe there is a space limitation. So that is streaming data. That means you scan it only once. See, unlike arrays, it is stored, right? You can scan it or visit it, any element, any number of times, unlimited number of times. On the other hand, in streaming data, right, you can only touch a data element only once, right? Yeah, so those are called one-pass algorithms, right? Streaming algorithms. So anyway, so we can encounter this even in the streaming set, but we will not cover any of the streaming algorithms. Okay, so we will assume we have a stored array, and we are finding the kth smallest element. It's also called the kth order statistic. You can also consider the kth largest element, right? It is similar to this, right? But we will consider kth smallest element. Note that this array is not a sorted array, right? This is an unsorted array. So you want to find the kth smallest element. So we will see a couple of cases, and then we will try to analyze some different variants of the problem. And we will stick to one variant and look at different algorithms to that variant. Okay. So if k is equal to 1, what happens? If k is equal to 1, you are finding the minimum element in the array. A dead easy problem, right? If k is equal to n, you're finding the maximum element in the array. Again, a dead easy problem. One scan, problem solved, right? Okay. What if k is equal to, say, 5? Fifth minimum element, right? Fifth smallest element. That is also a linear time. You can come up with a linear time algorithm, right? Scan the array 5 times, right? If k is a constant, then you have a linear time algorithm to solve the problem. But now consider, what if k is n by 2? Let's consider floor of n by 2. When you consider k is equal to floor of n by 2, it means you want to find the median element. What is the median element? The middle element in a set of numbers, right? If it is sorted, what will be the middle element if it is sorted? That's called the median element. That's the hardest case, right? That's the hardest case. And there are several applications where you might want to find the root nth element, or maybe n by third element, right? Something like that. So all those are generic cases, right? But here, easiest case is when k is equal to 1, k is equal to n, k is equal to constant, or k is equal to n by so n minus constant, right? Those are the easiest cases. Hardest is median algorithm, median finding algorithm. So think about this. So selection algorithm is related to the median finding algorithm. Because if you have an algorithm to solve the selection problem, you can find a solution to the median finding problem. So what about the other case? If you have an algorithm to find the median, can you use it for the selection problem? Okay, so think about that. Okay, fine. Next, let's look at the variance. Here we are interested in the kth smallest element. Okay, that's one element. What about the other? Are we interested in finding the top k minus 1 elements? Or what's the idea there, right? So we are not interested in any other element apart from kth smallest element here. Okay, if as a byproduct, as an intermediate step, we find top k minus 1 elements, okay, great, that's great. But it's not required that we have to find the top k minus 1 or k elements, right? We just want to find the kth smallest element. Okay, next, suppose as a byproduct we find the top k minus 1 elements. Should that be in the sorted order or not? We don't care. We don't care. So some algorithms as a byproduct might sort, right? Might give you the sorted order of the top k elements. But that's not the question. The question here is you just want to find the kth smallest element and you don't care about other elements. But if as a byproduct you get top k elements, whether sorted or not, that's good, right? But that's not what we are asking for here. Okay, there are a couple of algorithms. So except the last algorithm, we will look at every other algorithm. How many algorithms are covered here? 1, 2, 3, 4, 5. 5 algorithms, right? The first 4 are simple. We will cover them quickly. And the 5th algorithm takes a lot of time, right? We will spend a lot of time understanding 2 algorithms related to this, randomized quick select. And we will not have time to cover linear time algorithm for the selection problem. And probably you will also learn this at the graduate level, graduate algorithms and all that. Okay, it is out of scope. We will not cover the linear time algorithm. But you need to remember that there is a linear time algorithm. Because if in the interviews or anywhere, right, you should be aware what is the best algorithm for a particular problem, right? And that's this linear time algorithm. Remember that there is a linear time algorithm for solving the selection problem, though we have a linear time algorithm for finding minimum, maximum, right? K is equal to 1 or k is equal to constant, k is equal to n minus constant. But finding, say, k is equal to n by 2 was extremely difficult, right? But whatever might be the value of k, we can find this kth smallest element in linear time, n time. as if you're just scanning it scanning the entire array a couple of times and finding the kth smallest element, right? So this is a landmark result, a linear time algorithm, and this this is deep. There are like multiple linear time algorithms, not only one, and they try to reduce the constant factor of n, right? Theta of n means maybe it is 5n or maybe it is 7n, something like that, right? Constant times n, upper bounded by constant times n. And there are a couple of linear time algorithms. They try to reduce the constant further. We don't care. We just assume that, okay, there exists a linear time algorithm. Okay. Next. So top 4 algorithms are very naive solutions. We will cover them later, right? And then the most important takeaway from this decrease and conquer topic is your randomized quick select. Okay, leave the randomized part out. You can just consider quick select, but to make it faster, we will use randomization, right? Quick select is the core logic. To make it faster, you use randomized quick select. Okay. Now let's look at this column. So what does it say? So this says, while solving this problem, do you also get the k smallest items? We may or may not. Okay. So here we will find the k smallest items. Okay, so if you have a tick mark, it means we are finding the k smallest items. If you have a cross mark, then we will not. And what about this, sorted or not? Sometimes you can find this top k elements in a sorted order, right? So these are just the byproducts. We are not attacking this problem. We are just interested in the kth smallest element or the kth largest element. And where do you see this, smallest or largest? I mean, think about this. Top 10 frequencies, right? Or top 10 hottest topics, something like that. Or top 10 most viewed videos on YouTube, right? Top 10 most liked, posts on Facebook, so on. So there you consider top K, right? Top K. So here also you can generalize this problem to, we are interested in the top k, or what is the k smallest. It's related. All these are related variants. There are many variants, right? Okay. And we will understand this time complexity later. Okay. Let's start with the first 4 simple algorithms. The first one is dead simple, right? Sorting. Use any n log n times sorting algorithm on the array. You will get a sorted array and find the kth smallest element. Very simple. N log n. The time taken is n log n. If you use merge sort, or there is a version of quick sort that can solve the problem in n log n time, right? In the worst case, and heap sort takes n log n time, right? You have already seen the heap sort. So there are multiple n log n time sorting algorithms. Use any of those and you can solve the selection problem, n log n time. Okay, you get the k smallest elements also in the sorted order. But can we do better? Let's look at this partial selection sort. So what do you do here? So how does the selection sort work? Let's consider the first iteration of selection sort. The first iteration of selection sort gives you the smallest element in the array. The second iteration of selection sort gives you the second smallest element in the array. Right? Similarly, ith iteration of selection sort gives you the ith smallest element in the array. So use that for k iterations. Right? So you are using selection sort, but you're not running n-1 iterations. You're running it for k iterations only, and you will find the top k elements, k smallest elements in what complexity? So each iteration takes one scan of the array, that's n time. There are k iterations, k times n, kn. right? So as a byproduct, you're also kind of sorting the top k elements here. Make sense? So that's your partial selection sort. Simple algorithm, right? Kn. So if k is small, then this is kind of linear time algorithm, right? I mean, say k is constant. This is a linear time algorithm. What about this n log n? Irrespective of the value of k, the time is always n log n. So for many problems, the simplest thing to do is just sort and use the results, right? But that might not always give you the fastest algorithm. So you should be careful. See, this is independent of k. N log n is independent of k. But here, kn depends on k. But what if k is, say, n by 2? What happens if k is n by 2? This is n power. Can you tell me what happens if it is n by 2? N squared algorithm, right? If k is large, this will lead to n squared algorithm. Okay, so can we do better? That's not a good algorithm. Can we do better? So here is one more idea. Partial heap sort. Let's use heap sort. So what is the idea here? You have the array. Remember, any heap can be represented using an array also. So what you do is, using that array, create a min heap, right? You can create a min heap. In fact, though we did not look at this algorithm, you can construct a min heap or a max heap from an array in n time, right? In place, in n time. We did not look at this algorithm. We will also not look at this algorithm due to time constraints, but you can construct a min heap using an array in n time. Okay, I mean, like, what is the normal way, standard way? Take one element at a time and insert into the min heap. That will take n log n time, right? That will take n log n. But you can do better. You can construct a min heap in n time, right? So you can refer to books for this, but we do not have time to cover that algorithm here. Okay.
Professor, can I ask a quick question?
Yes.
On line 1, what does it mean in place?
In place means you're not using any asymptotically extra space. In place means you are given the array, you will modify the data structure in the same allocated memory.
Okay.
Right? In place means you're using the same space to modify the data structure and work on it. Out of place means, okay, you are using, maybe copying it or creating some other auxiliary space and using your data structures there.
Thank you.
Okay. See, once you have a min heap, what do you do? Simple. You want to keep popping the smallest elements, right? Call delete min once. You get the smallest element of the array. When you call the delete min for the second time, you get the second smallest element of the entire array, right? When you're calling it for the ith time, you are getting the ith smallest element of the array. So here you are interested in getting the kth smallest element. So call min heap k times, right? That's it. That's your kth smallest element. So as a byproduct, you are also getting the top k elements in the sorted order. Okay. So what is the complexity? Line 1, constructing a min heap, though we did not cover that algorithm here, we can do it in n time, linear time. We don't need n log n time. We can construct a min heap in n time. Next, delete min takes log n time. But you're calling delete min how many times? K times. So K log n. So the total complexity is n plus K log n, right? N plus K log n. So can you tell me which is greater here? Is n greater or K log n greater? Because we can always remove the term that is asymptotically smaller, right? We cannot decide on that. The reason is if K is say 1, then the complexity is n. The first term dominates, right? Term n dominates. Let me write it here. Dominates if K is small. The second term dominates when K is very large, right? Say if K is, can you give me an example when the second term dominates?
N over 2.
N over 2, yes, okay, N over 2. Right? Okay, so this is an example, right, where both terms are important. You cannot throw each of these terms out. Now, can you tell me if this is better than Kn? Is this better than Kn? K log n is definitely better than Kn, isn't it? K log n is definitely better than Kn. And what about n? Of course, like you have to scan, right? You have to scan. So you cannot do better than linear. Any algorithm, any deterministic algorithm cannot do better than n time, because you have to at least look at each and every element. So every algorithm has to take minimum n time. So n is okay. The remaining term is K log n. And as you compare, K log n is better than Kn. So this is definitely a better algorithm than the previous one. Okay. Next algorithm, online selection. So what is the idea here? We have a heap, right? We have a heap, but that's not the only way of using heap, right? We looked at heap here. One way of using the heap to solve the problem. But this is not the only way of using heap to solve the problem. There are other ways. See, here is another beautiful way. Now, let's think about this. Online selection. What is the idea here? You're given the array. So what do you do here? Let's look at line 1. Construct a k-sized max heap from this array. Look at the difference. That was a min heap, right? When we constructed a min heap for the entire array, when you keep deleting min elements from it, you get the smallest, second smallest, and so on. So here we are considering max heap. Why do we need max heap? When we are interested in the smallest elements, why are we interested in max heap? Okay, but the difference is, see, that heap algorithm, the size was n. The size of this min heap was n. What is the size of this max heap? It is k. So it's a different data structure. I meant it serves a different purpose, right? It is not exactly same as this. The size of this was n, and we use a min heap, but the size of this heap is k, and this heap is a max heap. And you will understand why we used k as the size. Let me add a diagram. So this is your k-sized max heap, right? construct a k size max heap from the first k elements. Look at this, not from the entire array. So how can you construct a heap from the entire array, a k-sized heap from an n element array, right? So here we are just constructing this from first k elements of A. Okay. Now the remaining elements are still in the array. So you had k elements here and the remaining n minus k elements here, right? Now what do? Think about it. Look at the loop. I is equal to k to n minus 1. That means you scan each and every element in the remaining array. Let's consider this as your AI, right? AI, the ith element you're scanning. If that is not more than the heap's maximum, if that is not more than the heap's maximum, then you will insert this into the heap and delete max. You keep doing this for this entire remaining elements. Can you tell me what is the logic behind this? And why do we do this?
Is what's left in the array the k smallest elements?
Exactly. After doing this, you will have the k smallest elements. Right? So after scanning the remaining elements, and you run this logic. If A of I is not more than the heap's maximum, insert one element into the heap, delete max an element from the heap, so that the heap is always of size k. Finally, at the end, you will have k smallest elements here. Can you tell me how? Why? So let's focus on this line 3. If A of I is more than the heap's maximum, what does that mean?
It means it's bigger than a number you've already put into the heap, so it's not going to be one of the smallest numbers.
Exactly. So suppose you have k elements here. If A of I is bigger than the heap max, right? The max element here, max element is at the root, right? Checking that is constant time. So if A of I is greater than the max element, that means it is greater than all elements in the heap. That means it is definitely greater than k elements. If it is definitely greater than k elements, it cannot be one of the smallest k elements. Correct? If A of I is greater than heap's maximum, it means that there are k elements less than A of I. For that reason, A of I can never be one of the k smallest elements of the entire. Hence, you throw that off. Right? Suppose A of I is less than or equal to the max element of the heap. Maybe it is one of the top k elements. So what do? You insert that element into the heap. Now that there are k plus 1 items in the heap, right? But you're interested in only top k. So you remove one maximum element there, delete max, right? Which is impossible to be one of the top k. So you insert A of I and you delete max. So that this heap, so once you have scanned till A of I elements, it means this is the smallest k elements from 1 to I, A of 1 to I. Make sense?
Yes.
So you keep repeating this logic until the dead end. So at the end, you will have the top k elements in the heap. If you want to find the kth smallest element, what do? Once you have this heap, just remove the topmost element, the root element, that is delete max. That is your kth smallest element. If you want all the top k elements in the sorted order, you can go ahead deleting multiple times, right? But if you just do a scan, you will get the top k elements, but not in the sorted order. So depending on your application, either you might want them in the sorted order, you might not want them in the sorted order, or you don't care about the top k minus 1 elements. You are just interested in the kth smallest element. That you get when you call delete max just once, right after this process ends, after this loop ends. That's your kth smallest element. And what is the complexity? Let's look at the complexity. The complexity is k here. As I said, you can construct a heap from n elements in n time, a linear time algorithm, right? For constructing a heap. So we use that linear time algorithm, k-sized heap, theta k. Okay, so what do you do here? So how many elements are there here? N minus k times, right? Insert takes log n time, delete, log k time, delete max takes log k time. Why log k? Because there are only k elements in the heap, right? Log k for insert, log k for delete max, but you do this n minus k times. So you can say it is upper bounded by n log k, right? K, n log k. And what about this? Delete max is log k. We don't really care, right? Log k. So what is the total complexity? You can write it as k plus n log k. I mean, anyway, you don't care for this. K plus n log k. So why didn't we write k plus n log k? Why did we write just n log k?
Is it because that's always going to be the most important term?
Right, n log k definitely dominates k, right? K is at most n. Remember, k is at most n. What about n log k? I mean, you don't care about what happens when k is equal to 1 or 0. Those are tiny values, right? But so in general, so let's consider k is greater than or equal to 2. This is at least n, right? N to n log n. So it is in the range n to n log n. K is always less than or equal to n, so we don't care. Okay, n log k. So n log k is a good algorithm. Is a good algorithm, right? Okay, so that's about the first 4 simple algorithms. Now let's look at randomized quick select. So think about this. Till now, we have been in the world of deterministic algorithms, I believe, right? We never looked at any probabilistic algorithm, right? Only in the world of deterministic algorithms. So what is deterministic? That means the kind of the fate is already decided, right? The I plus 1 step is decided. If you give the input, 1 trillion step is already decided. If you give the same input, you get the same output following the same steps. Step 1, step 2. There is no change. That is called determinism. And what is non-determinism? every time for the same input, the steps can vary, right? So there have been debates on whether the word is deterministic or non-deterministic and all, right? The first shock to the word came through quantum mechanics. So till then, everything was considered deterministic. Newton thought the word universe is deterministic. Einstein thought the word is deterministic, right? But from quantum mechanics, we thought that nature at the tiniest level is not purely deterministic. It is implicitly, inherently probabilistic. It's based on probability. You cannot even determine the location of an electron, right? You can only give a probability. Okay, so this probabilistic analysis, or you can also consider them as randomized, right? Randomization is one type of probabilistic, right? Okay. So when we say random, we typically assume uniformly random numbers or like whatever. And that is one type of probability distribution. But probability distribution itself can be kind of infinite variety, right? So we know that the nature itself is probabilistic and all. So here also in algorithmic problem solving and computation, we consider randomization too. We consider probabilistic algorithms too. Because many times we are not interested in deterministic output, or like we don't care like what are the steps, right? So there are two types of probabilistic algorithms, or you can say randomized algorithms. One is you use randomization, but you get 100% correct output. Always 100% correct output. But, right, the steps in which you go here and there can vary. So there is another type of randomized algorithms where the output itself can be correct or incorrect depending on probability, right? So here, what is the idea here? Quick select. We say that the time it takes is theta n in average, right? The average time is linear. But in the worst case, it can take n squared time. The worst case is n squared time. Okay, the worst case is n squared time. That means, I mean, definitely it works, right? But the time taken depends on that, you know, which random numbers are used and all that. Okay, so this is not deterministic in the sense we do not know step by step, you know, what should I say? Like we do not know the execution of the algorithm at every step. It depends on the randomized algorithm. It depends on randomization, right? However, we know it solves the problem, but the runtime can wait. Okay, we will focus on this algorithm. I mean, this problem, there are two algorithms we will see, and we will not cover linear time algorithm. But in the future, if you encounter any problem like this, selection problem, you should know that there is a linear time algorithm, and maybe you can invoke that linear time algorithm as an API, like a function call, right? Remember, right? So for theoretical analysis, you can use it, but it is probably slightly complicated, and it might take a bit more time in practice. Probably that works when n is huge, that would be faster in practice, but normal values, so practical values of n, right, which fits in a laptop and all, probably quick select is probably fastest. Okay, let's skip all this. Let's move to randomized quick select. So what are we trying to solve here? We want to find the kth smallest element. So we will understand this logic through a diagram. So we are given an array, unsorted array, say, and the array values are something like this. See, a of 1 it might be 100, a of 2 might be say 87, a of 3 is 96, so on. The height depicts the value. So it's not in the sorted order, right? Suppose you want to find the kth smallest element here, kth smallest element. So how do you solve the problem? Before that, before solving this, right, this quick select algorithm uses an intermediate step. It calls a function called partition. We need to understand that partition logic first, right? We will focus heavily on the partition logic, and that partition logic will be subsequently used to find the kth smallest element. Okay, so let's understand partition logic. So what is the meaning of partition? So this is a different problem, right? See, one problem calls another problem. So we want to understand partition problem now. So what is the partition problem? So you are given an array and say you're given a pivot. You can consider the first element as the pivot or some element as the pivot, right? We will analyze this later. So let's consider this as the pivot element. Partition means this. You want to partition the array in such a way that all elements less than or equal to pivot will be to the left of pivot. All elements that are greater than pivot will be to the right of pivot. So after calling this partition function, what happens is all elements to the left of pivot will be less than or equal to pivot. All elements to the right of pivot will be greater than pivot. Make sense? So that is the meaning of partition. Suppose this is say 37. It means that all elements to the left of it will be less than or equal to 37 after calling this function. All elements to the right of this element in the array, right, will be greater than 37. So that's the meaning of partition. So we want to introduce this function or problem and use the algorithm to do this partition as an intermediate step for finding the kth smallest element. Okay, so at first we will assume that there is a partition function. Assume that there is an API or a function called partition that does this. Later we will see, how. So the two algorithms for partition. But right now, assume that there is an algorithm that can partition the array based on pivot element. So typically, normal textbooks consider first element as the pivot. So if you have an array like 43, 89, 10, 50, so on, typically you consider the first element as the pivot. So 43, that means after partitioning, 43 will be in its correct location and all elements here will be less than 43, 10, 37, whatever, right? They need not be sorted. They need not be sorted. They are just less than 43. They need not be sorted. And all elements here will be greater than 43 and they need not be sorted. Okay, we don't care about sorting. We just want to make sure that 43 goes to its correct position and all elements to the left are smaller, right are greater. Simple, right? So the standard books use first element as the pivot. We can use a random element as the pivot, right? But as of now, you can assume first element is the pivot. Now let's see. So randomized quick select. So you are given an array. So this is a subrange L to H. you want to find the kth smallest element in this array, subarray, whatever. So what is the idea here? If L is equal to H, then return A of L. So assume that K is the initial call to this. What is the initial invocation? You call this A of 1 to N, right? 1 to N. And you want to find the kth smallest element, and K is in the range 1 to N, right? 1 to N. Okay, so make sense? If L is equal to H, then return A of L. Return A of L. So why did we return A of L? That means, so kth smallest element always exists, right? If K is in the range 1 to N, it always exists. There should be one first smallest element, second smallest, third smallest, so on, right? Okay, next. So this is the base case. And let's see the recursion case. In the recursion case, what do? You partition the array. You partition the array. And how do you partition? You need a pivot element for partitioning, right? We will use randomized partition. Randomized partition. So you had this array. After random partition, what happens? A random element will be considered, right? Say 283. Now 283 will go to its correct position, and all elements to the left are less than 283, say less than or equal to, and all elements to the right are greater than 283, right? So you partition the array based on a random element, and what do you return? You return the index or position of that partition where the array has been partitioned. So here, if it is say 17th position, right? Index number 17, you return 17 here, right? You return 17. Make sense? You just return the position or location or index number of that partition point. Now, consider this. Size is equal to S minus L plus 1. So you have L here. Say you partitioned at S, right? Say S. And this is high. Low index. L means low. H means high index. S means the point of partition. Now you consider size is equal to S minus L plus 1. That is the first half. It's not really half, right? It can be variable size. That's why we are learning variable size decrease here, right? This is need not be half. It can be here, it can be here, anywhere, right? It depends on the random algorithm. So sometimes the partition can be worse, that is somewhere to the end. A good partition means, right, an element that is selected that is almost at the midpoint. Then you have two subarrays that you will recursively solve, right? We will see that. Now size is equal to S minus L plus 1. This is equal to the length of the first part is size, that is S minus low plus 1. Now what do? If K is equal to size, the kth smallest element that you wanted to get, right? If that is equal to size, then definitely A of S is your kth smallest element, right? See? A of S will be the kth smallest element. If the number of elements in the first part is equal to K itself, then that's your answer. So return A of S. If K is less than size, if suppose size is say 50, if K is say 10 smallest element, 10 is less than, you know that all elements in the first part, right, in the first part are less than or equal to A of S. So what do you need to do? All the smallest elements are in the first part. In the second part has more elements, larger elements. That's the meaning of partition, right? Smaller elements are in first part, larger elements are in the second part. So if k is less than size, your kth smallest element is in the first part. So search in the first part. So the array is L to S minus 1, low to S minus 1. It's definitely not like your binary search, right? But S is not the midpoint. That's it. This is like your binary search. The only difference, lines 5 to 10 are like your binary search. The only difference is that S is not, need not be the midpoint. If k is less than size, kth smallest element is in the first part. So recursively call randomized quick select of the kth smallest element in the first part of the array. If k greater than size, then k is definitely greater than all elements in the first part. So you need to find k minus sized smallest element in the second half, right? So think about this. Suppose suppose size is 50, k is say 80, k is 80, size is 50. So definitely the 80th smallest element will not occur here. It should occur in the second part, right? So if you remove all these elements, what happens? 80 minus 50 is 30. So you want to find the 30th smallest element in the second part of the array. Make sense? That's it. That's your randomized quick select. So there are two parts here, right? The first part is randomized partition. The partition function makes sure that you are dividing the array into part 1 and part 2, right? Like this. So the division point is S. And then you will compare k with the size of first part. If it is equal to the size of first part, then the partition point itself is the kth smallest element. If k is less than the first part size, then definitely the kth smallest element should occur in the first part. So you recursively call that's a problem. If k is greater than size, then it cannot occur in the first part. So you remove all those elements in the first part. So k minus size. So find the k minus sized smallest element in the second part. That's it. Questions? Questions?
Yeah, Professor, I do have a quick question.
Yes.
I'm having a hard time imagining this and figuring it out. I'm going to have to try to code it and work through it. Do you have pseudocode for the randomized quick select so I can try to implement it?
We will see
Okay,
the
because-
randomized partition algorithm.
Yeah, because I'm having a hard time wrapping my brain around this. I might
No,
have
no,
to
no. So
actually.
here assume that there is one API that solves the problem, right? We will
Yeah.
look at it later. I didn't want to go deeper here first and then come to quick select. Right?
Yeah, no, I understand. I'm having a hard time understanding why the size is relating to where the kth element is, but I think I need to just trace it out on paper and then I can see it better.
I see. See, the partition, you know that the partition divides the array into, say, two parts, right?
Greater than and less than the initial
All
partition.
are greater than or equal to, say, this element. and all these elements on the right are greater than, sorry, this is less than or equal to the partition element, and all
Right.
the elements to the right are greater than the partition element.
Yes,
Right?
I
So,
got that. Yeah.
yeah, suppose the index is 20 here. It automatically means that, see, if you're interested in the top 20 elements, right, it should occur here.
Yeah, I get that. But what if your random partition is the first number, like you said the textbooks do, and that ends up in position 15, and you want the top 20? It's going to be split. I guess that's what I'm struggling with.
Right. Okay. So you want, repeat again, what do you want?
So say you want the top 20, but the first position the first partition point you pick is A0. And that ends up in, when you run the randomized partition, that ends up in A15, but you want the top 20.
Right. Okay. So you want the 20th smallest element, right? But the partition happened at index 15, right?
Oh, wait, okay. I'm misunderstanding. You don't want all of the top 20, you just want the 20th one.
Just 20th element.
Oh, I was thinking you want the top 20 and it was going to span the partition, but you just want the one element that's
Yeah,
at the
so
20th
I just want the
position.
20th smallest element.
Okay, I got it now. Thank you.
Right? So here we are not caring for what happens to the first smallest, second smallest, so on up to 19 smallest. We don't care.
Now I get it. Now I get it. Thank you.
Okay. So that's about quick select algorithm. See, this will take time. These are hard algorithms, right? Selection as well as partition, right? So now we will look at partition algorithms. So there are two types of two algorithms given here. One is Lomuto partition, another is Hoare partition, right? Let's scan them one by one. So randomized partition. For simplicity, assume that you don't have this code. So just you assume that you have this code. Lomuto partition. You are given an array, subarray, whatever. You're partitioning this subarray using first element as the pivot, right? First element is the pivot, right? So there are a couple of problems when you consider first element or a specific element as a pivot, like first element or say last element, something like that. So what we do is we construct randomized partition. In randomized partition, we find a random element in this subarray. From low to high index, choose a random number. You will get an arbitrary, right, random index in this low to high. Then you swap that with the first element. So the random element now became the first element, right? Random element became the first element. Now call the Lomuto partition. So here A of L, though you're considering the first element has been selected using a random process, right? This is important. Suppose you didn't have this randomized process. You always chose the first element, right? When you code it and run it multiple times, you will see that it might not give you the best performance. And theoretically, you can prove this, but the complexity analysis is a bit hard because you want to use this probabilistic analysis of time complexity and all, right? Though we will not look at all that probabilistic analysis, right? There's a lot more analysis, to show that this is way better than choosing the first element, right? We will not consider all that analysis. Just assume that this selection of a random partition element is the best way to proceed. Hence, we have this randomization, and we swap with the first element, and we always go with I mean, this one considers the first element as the pivot element and partitions it. Okay. Now, so the first three steps are simple. Let's go to low-motive partition. So how does this algorithm work? First, we will try to understand this algorithm via an example, and then we will come back to the code. So here is your array. So we have considered how many? 1, 2, 4, 8 elements. This is the L. The first element is the L here. Okay, so how do I minimize all these tabs? Okay. So the first element is low index. The last element is high index. So initially you invoke, right? So either you invoke on say 0 to n minus 1 or from a of 1 to n, whatever. So that that 1 will go to L, n will go to h, and so on. So those subarrays will be considered. Anyway, so this is your low index, this is your high index or location, position. And we are considering the first element as the pivot element in the low motive partition. So pivot is the first element, that is 3. A of L is 3. And then you have two variables, I and j. And what do they represent? So I keeps track of, okay, let's say something like this. At the end of this partition, see, at the end of this partition, what happens? Look at this. The pivot element shown in yellow remains here as the first element. And then the blue elements are all the elements that are less than 3. So here I have just considered unique numbers for simplicity. Okay. So it's easier to analyze only unique numbers for simplicity. All blue elements are less than 3. All red elements are greater than 3. The pivot element. Okay. Then we do a final swap. We will have all blue elements to the left of yellow, all red elements to the right of yellow. Okay. And that's your partition. So 3 goes to its correct position here. Okay. Makes sense? Now, what is the point of I variable? I variable keeps track of the last element that is smaller than pivot element. And j keeps track of the last element greater than pivot element. Okay. So with this, let's start. So what do you do initially? Let's go back to the code. See here. Pivot element is E of L. You start I with L, and j will start with L plus 1 to h. Okay. I is the first element, points to first element, and j goes in a loop from the second element to the last element. Okay. So let's do that. Areas. So I is at the pivot element, so pointing to 3, and j starts with 8 here. Now what do you do? So j points to 8, right? 8 is greater than this pivot element 3. 8 is greater than 3. When 8, the a of j is greater than pivot, keep incrementing j. So 8 is greater than 3, increment j. Now j goes to this. 6 is greater than 3, increment j. 7 is greater than 3, increment j. 1 is less than 3, so stop here. Okay, so when A of j is less than or equal to pivot, what do? You stop. You increment I at this point. I points to 8. Now look at what's happening. I is pointing to a value greater than 3. J is pointing to a value less than 3. This is the right time to swap. Swap A of I and A of j. What happens? 1 goes here, 8 comes here. Right? So after this swapping, the blue element that was less than the yellow value, right, 3, is at its kind of correct position. Correct position in the sense it should be at the left, right? So after this swap, see, all the blue elements are to the left, all red elements still here are to the right. That's what we want to do. And we want to keep increasing the sizes of this blue subarray and red subarray. So after this swap, we keep continuing with j. J goes to the next element, points to the next element. 5 is greater than 3. Again, move j. 2 is less than 3. So stop. Stop here. So when you see that A of j is less than or equal to pivot, what do? You increment I and swap A of I, A of j. I mean, that's the same pattern everywhere, right? Increment I goes here. Now look at this. A of I points to a value greater than 3. A of j points to a value less than 3. So this is the right time to swap. When you swap, what happens? 2 comes here, 6 comes here. Now you see that the subarray of the blue subarray, right, is expanding, and the red subarray is also expanding, and blue subarray is always before the red subarray. That means the smaller elements are always before the larger elements. Okay, continue this process until you hit the dead end, right? So j increment, okay, so 6 is greater than 3, so increment. 4 is greater than 3, increment. Now what do? So this is the point when you stop. J is equal to h plus 1, right? You cannot keep incrementing forever. So here is where you stop. Now you have already partitioned, right? All the blue elements are to the left, all the red elements are to the right. The only thing you need to make sure is that the yellow element, the pivot element, comes after all the blue elements, right? A of I or I points to the last position where the element is less than 3. And j points to the last element where A of j is greater than 3. So, but currently j is out of bound here. So we are interested in this I, the last cell of blue subarray, right? Swap yellow and the last cell of blue subarray. Now you see that 3, right? Pivot 3 goes to its correct position here. 3 is at its correct position. The rank of it is 3 here, right? So it is at its correct position, and all the elements to the left are less than 3. All the elements to the right are greater than 3. This is partitioning. And you see that the left subarray and the right subarray, they need not be sorted. Our aim is not sorting. Our aim is to make sure that we partition the entire array based on this element, pivot element, such that the left elements are less than 3, right elements are greater than 3. Make sense?
Yes.
So this is your low. Okay. Let me move to next algorithm. Next, we will look at Hoare partition. See, this is the logic for Hoare partition. Okay, so I won't go to each and every line in the pseudocode, right? You can derive the pseudocode once you understand the logic. Okay, so pivot is A of L, I is equal to L, J is equal to H plus 1. So this is last element plus 1. That means probably we will be decrementing J and we will be incrementing I here. Right? So this has a different logic for partitioning. Okay, let's try to understand it using an example. Again, the same array. L is this, H is this, pivot is the first element, I points to the first element, J points to H plus 1. So it is outside the array. Remember, in low-moto partition, J was pointing to the next element of I plus 1, right? So here, J is pointing to H plus 1. It's outside. So there, J was incrementing in low-moto partition. Here, J will be decrementing. Okay, we will see that. So what is the idea here? The same idea. Remember all that blue cells, red cells? We will use the same idea. So increment I, right? Increment I, you get say 8. Whenever A of I is greater than the pivot element, you stop. So you stop here. So keep decrementing J. See, J becomes this. 4 is greater than 3. So decrement J again. 2 is less than 3. So you keep decrementing J until you see that A of J is less than pivot. Similarly, you keep incrementing I until A of I is greater than pivot. See, like what is the meaning of this? A stopped at here, J stopped at here. What is the meaning of this? The left element is greater, right element is smaller. Oh, this cannot happen, right? So we swap. Now we are swapping A of I and A of J. 2 goes here, 8 comes here. Again, so keep scanning the array, incrementing I until you find an element that is greater than 3. Keep decrementing J until you find an element that is smaller than 3. Okay, so let's try. Increment I. This is greater than 3, right? So you stop. Decrement J. J points to say 5. So this is still greater than 3. That's fine. Decrement G again. You find that 1 is smaller than 3. This is where you stop. Right? So see, 6 is greater than 1. 6 is greater than 3 here. 3 is greater than 1. So these are out of positions. So swap. Make sense? Now 1 is here and 6 is here. Look at the order of these blue and red cells. Remember, in low-moto partition, we were scanning from left to right, and the blue subarray was increasing in size, red subarray was increasing in size. But here in whole partition, we are incrementing I from left and decrementing j from right. You see that the blue subarray is increasing in size and this red subarray is increasing in size from the right end, right? And when is the stopping point? When you have scanned all the cells, right? So keep doing it. So I goes to, okay, after swapping, A of I is 1 here, A of j is 6. Increment I. So 7 is greater than 3, you stop. Decrement j. J points to 7. 7 is greater than 3. That's fine. But again, decrement j. 1 is smaller than 3. This is where you stop. See, you keep decrementing j until you find an element that is smaller than the pivot, right? That's the logic. And what do you do here? You see that, okay, so you see that j, for the first time, j is less than or equal to I. That means there is a crossover. Always I was less than j, right? See, I is less than j, I is less than j, I is less than j here. So j will be less than or equal to I for the first time. That is the crossover point. I greater than, right, j, or j less than or equal. This is the crossover point. At this crossover point, what happens? It means that you have scanned every cell in the array and made sure that it goes to either the blue subarray or the red subarray. That means it has been partitioned properly. Okay, so this crossover is the end process of scanning and checking, comparing, swapping, whatever. This is the end, right, process where the end happens. At this point, what you do is you do a final swap. Swap the pivot element and A of j. So here j represents the last cell in the blue subarray. As in your low-modo partition, right? You want to swap with the last element in the blue subarray. Now red goes here and you have all elements to the left of 3 to the left, all elements greater than 3 to the right of 3. That's your partition. This is called core partition. Okay, so let's quickly look at the code. Right, while true. So what is the meaning of this? Keep incrementing I until A of I is less than pivot. So A of I is less than pivot. If it is less than pivot, so this is A of I, right? A of I is less than pivot. Keep incrementing I. Similarly, okay, so if I is equal to H, you break. Of course, if you hit the right dead end, you have to break. So what happens here? While pivot is less than A of minus minus j, that means keep decrementing j when you see that pivot is less than A of j or A of j is greater than pivot. So that means, so this is I, right? For j, you keep decrementing j, when you see that A of j is greater than pivot. So that means all these are greater elements, right? All these are smaller elements. If they are smaller elements, keep incrementing I. On the right hand side, if all the elements you see are greater than pivot, that means you can keep decrementing j. There is no problem. You can keep scanning. That's the meaning, right? You stop when you see that A of I is greater than pivot and A of j is less than pivot. right? When you come out of this while loop, you see that A of I is greater than pivot, A of j is less than pivot.
Professor?
You swap here, right? So just a minute, right? Stacey?
Yeah, sure.
So you swap here at this point. So this makes sure that you added one cell to the left subarray or the blue subarray and added one cell to the right subarray or the red subarray. You will not swap, right, when there is a crossover. This is the crossover point. Crossover point. When crossover happens, that means you have scanned the entire array and you do a final swap with the pivot and E of j and return j. J is the point of partition. Okay, yes, yes, please. Okay, tell me questions.
I just have a comment. The partition sounds, the partition technology sounds really familiar to me. Is it possible to partition these two technologies, techniques, not technologies, techniques also used in other sorting algorithm? Because I read about these two exact partition technique, but I forgot, what kind of application is used.
Right, so this partition logic, right, can be used as part of your quicksort. We will study quicksort probably in the divide and conquer, right?
Oh yeah,
Partition logic is used. Either you can use Lomuto partition or Hoare partition. Both take linear time because they are just scanning elements one by one, and they won't repeatedly scan an element multiple times. So it is a linear time algorithm for partitioning, Lomuto partitioning or Hoare partitioning. And we do an extra layer of randomization here that will give you a randomized partition, either using Hoare partition or Lomuto partition. Any of these can be used in quicksort, and it can also be used for the selection algorithm, right? Make sense? Okay, questions?
Yeah, thank you, Professor. It reminds me, I think I was studying a quicksort a couple years ago, and then I forgot about it. But the partition algorithm just really stick out to me. But I forgot what was actually used before. Yes.
Nice. Okay, good. Yeah, Stacy has a question in chat. Thought that using break isn't good practice, that the loop should stop based on data. So using breaks are fine, right? And for many conditionals, you have to use break. So what is not good programming practice is using go-to statements. Remember, we had to use go-to statements in some of the earlier languages and all. So that's not a good programming practice, but using break is totally fine, right? That's totally fine. You're coming out of the loop, and based on a condition, you have to terminate the loop. So that is totally fine. So any questions? See, this is an important, very important problem, right? The partition itself, because in quicksort, we will not cover this again. We will say that we have already covered partition. We will just focus on quicksort logic. But this partition is also part of quick select, randomized quick select, right? So try to implement this quick select algorithm and later quick sort also. But when you used a randomized partition, as discussed here, not just the first element as the partition, but the randomized element as the partition element, right? You will see that in practice, it runs a lot faster. All these are linear time algorithms, right? Partition takes linear time, and Lomuto partition takes linear time, Hoare partition takes linear time, but I believe Hoare might be slightly faster than Lomuto partition in practice. Okay, so try that out. So do all these experiments and randomized quick select uses partition and uses recursive quick select like your binary search. But this is not binary search because that point S need not be at the middle point, the median, right? It can be anything. In the worst case, what's the runtime of this algorithm? N squared, right? Worst case is N squared because the element you select for partitioning can be like this, right? So after partition, you divide it into only two parts. I mean, the first part is just one element. So this took linear time, theta of n for partitioning, and you recursively call the quick select on this. And again, you do partitioning here. You're partitioning only one element. And then this takes theta of, say, n minus 1 time, and keep doing it until you hit the dead end. So that is, say, theta 1. So the summation of all this is n squared. That is in the worst case, but it's very likely that this case will not occur a lot of times because we are randomizing it, right? So with high probability, it does a very good partitioning, and the quick select runs very fast. So that's the name. That's why the name quick select. And even in quick sort, why did they use the term quick? Because in practice, quick sort is used in libraries, the sort function, right? That is the most commonly used sort function in all programming languages. Quick select, quick sort, and that ultimately uses the partition logic here. Okay. So we will stop at this point, study all this. We didn't have time to go over the second, another algorithm, right? Josephus problem. We will cover divide and conquer algorithms in the next session onwards. Okay, thanks a lot. Take care.